In this lesson, we will build an intuitive picture of liquefaction and subsidence caused by earthquakes. We will see what liquefaction is, how lateral spreading works, and how broad-scale subsidence can warp landscapes. Let us build a simple cross-section. The lower layer is saturated sand and silt. During strong shaking, pore water pressure rises and pushes grains apart, so effective stress and shear strength drop. The soil behaves like a liquid. At the surface, liquefaction leaves clear clues. Sand boils erupt as pressurized water carries sand upward. Cracks open, and the ground spreads laterally toward free faces like the river. This lateral spreading stretches the surface and drops blocks downward and outward. Structures on liquefied ground can sink or tilt. Here is a small house on the surface. As the soil loses strength, the foundation settles unevenly and the house tilts. Real earthquakes illustrate these processes. In 2010, in Haiti, young coastal sediments liquefied, sand boils erupted, and lateral spreads damaged the port. In Christchurch, New Zealand, in 2011, massive liquefaction inundated neighborhoods, and the ground settled by tens of centimeters to over half a meter in places. Subsidence can come from different mechanisms. 1. Tectonic subsidence from fault slip. 2. Distributed compaction of soft soils during shaking. 3. Ground failure, such as liquefaction that rearranges material. At regional scale, slip at depth can create a bulge and a trough, gently warping the land surface. How do we recognize these effects? In the field, we map sand blows, fissures, and tilted objects. From satellites, radar interferometry can detect broad patterns of subsidence or uplift, and drones can map cracks and sand vents in detail across floodplains. Geotechnical tests help evaluate liquefaction potential. A cone penetration test measures tip resistance with depth. Loose, saturated sands show low resistance and are prone to liquefy. Similarly, standard penetration blow counts correlate with resistance to liquefaction. Subsidence can change coastlines. When the land drops, more area becomes intertidal or submerged. That can drown marshes, create new tidal flats, and increase saline intrusion. For planning and rebuilding, liquefaction susceptibility maps identify high-risk zones. These guide land use, foundation design, and soil improvement to reduce future damage. In summary, liquefaction happens when shaking raises pore pressure in saturated, loose soils until they lose strength. Surface signs include sand boils, fissures, and lateral spreading that can sink or tilt structures. Subsidence ranges from localized settlement to regional warping after big earthquakes, altering drainage and coastlines. Field mapping, radar interferometry, and geotechnical testing together inform hazard zonation and resilient design.